Hello everyone, welcome to this video. In this video, I would be explaining my latest project in which I have trained a diffusion language model from scratch on Shakespeare text. So I would be giving a walkthrough of this project, but before that, I would be explaining some important concepts on how diffusion language model works and how they are actually different from traditional ARMs or autoregressive models. Now, to actually understand and make use of this video, you must be aware of some prerequisites. So these are, first, you should have the knowledge of PyTorch. You should have written some models and trained models in PyTorch. Second would be attention mechanisms, because since diffusion LLMs primarily work with transformer architecture, you should have knowledge of attention mechanisms and transform architecture. And third would be the basics of diffusion. See, diffusion language models are a little bit different from traditional image diffusion models. So you should know a little bit of the diffusion process. If you don't, I would be explaining the traditional diffusion process also in a brief. Yeah. So let me start this video by explaining the image diffusion process. It is very necessary for us to understand the image diffusion process first. Later on, we can jump to diffusion elements or language diffusion. So in layman terms, how does image diffusion works? We basically have two processes. First is the forward diffusion process, where we gradually add noise to image. And you can see this is a clear image. We add random noise to it, and this becomes a completely noise image. And then the reverse diffusion process, we do the opposite. Now, the actual predicting or actually generating images is in the reverse diffusion process. So let's take a model. Let's take this is a model. It has some weights W. Okay. So what we essentially do during the training is that we would actually take this clean image and randomly sample a time step. So time steps are basically from t equals to 0 to t equals to 1. So what I would do is I would randomly take any time step. Let's say this one. Okay. So this is, let's say, t equals to 0.2. Okay. So now in this, I would be taking the clean image. I would be adding some noise to it. And then I would be giving this particular image. Okay. So this is a little bit corrupted image. And I would be asking the model that, hey, you tell me how much noise did I add into this image so that if I subtract that particular noise, I get this image. Okay. Then we would actually take a look at the noise and we'll see how much the model was wrong and then update the weights accordingly. So this is the training process. So we can actually take any time step from it. The image would be same, but in this way, the model actually learns that, hey, what are the different stages, and it can actually, take the image from any particular stage and make it back to this proper image or image to a high probability area. So essentially what the idea of diffusion is that to generate images, we would actually take some random noise. Now, generating this random noise is easy. We can generate it with a random PyTorch function. And then we apply this model, which generates the noise, which we actually subtract. And gradually, we come to this clean image. So this is the whole idea of image diffusion in layman terms. Obviously, I did not go into maths. I did not go into details. But yeah, this is the layman idea of how image diffusion models actually work. This would be very necessary for us in understanding language diffusion models. Okay, so let me also explain how autoregressive models like your chatbots, GPTs, etc. work at the low level. So the first part of training an autoregressive model is pre-training, where we just give it the task of next token prediction. Let's say I am writing something like I am. So I am given essentially two tokens to the model. Okay. And now I would be asking the model to predict the third token. Okay. So let's say third token is okay. So now the model has predicted the third token. Now I would be taking this entire sequence and giving it to the model again. Now it would be predicting the fourth token. Let's say it is something like boy. I am a boy. Now this whole thing would be going again into the model and it would be predicting the fifth token. Let's say the fifth token is full stop. Okay. And now the last token, to end it, it would predict something like end. And now this whole LLM would end. So this is like the low level overview of how autoregressive model works. Obviously, this is not, there are a lot of components like the training pipeline and the generation loops, etc. But I would not be going into detail. But so the main idea it is that we would be giving essentially the input and asking it to predict the output one token at a time. And every new token predicted would be going again into the model. We would be recalculating the attention mechanisms and predicting the next token. Till the end token is predicted, then we actually end the flow and we have our output. This is for the pre-training, and for fine-tuning also we do something like this, but it is more like we give the prompt, like it is something like user. Then I would ask basically like who is the okay, please forgive my handwriting. I am a little bit new to this drawing board. President of, let's say, India. Okay, then we would be actually ending this. Okay, user. So this is the first part of the prompt, and then we would be essentially starting it with like the maybe the start token, and then it would start generating the output and then the end token. Now this is like the prompt template, this or the chat template. This varies with different models, but you can make something like this. Okay, this is actually how chatbots work. This step is in the fine tuning, but yeah, the pre-training or the core idea is still the same. In this also, this would be a token. These all are tokens, and it would be asked to predict one token. Now, after the token is predicted, everything goes back. Attention is recomputed, then next token, till the end token. So this is how autoregressive models work, one token at a time. Okay, so in this part, we will be discussing about diffusion LLMs, or well, diffusion LMs. This is not a large model. So let's assume we have our model. This is, I am defined it by M, and this model has a sequence length of 14. So it can essentially accept at the max of 14 tokens in its entire context window. Okay. So I have actually given something like, hi, I am a good boy. I love to play. This is a full stop. So this model has some weights, W. This would be easier to understand. Now, for the training of this diffusion language model, what we do is we take these tokens and we replace them with the mass token. Okay. The mass token is in the vocabulary and all. So diffusion language models also work kind of similarly to image diffusion models. Like in the image diffusion models, we notice that we have time step from t equals to 0 to t equals to 1. Okay. And between them, we can have multiple steps. Let's take let's say it has like 4 steps. Okay. So this step would be consistent. So in the step 1, we would be randomly masking a few of these tokens and replacing them with the mask token. Okay. Let's say I have a sampler and it masks this token, this token, this token, and this token. Now these tokens are masked and replaced with this particular mask token. Okay. So this also goes to the mask token, and this also is replaced with the mask token. Okay. So now these tokens are masked. Now we would ask our model, we would actually give this particular input string to it and ask our model, this model, to predict the original, this tokens. Okay, so obviously these would stay the same, but we would be only taking notice of these mask tokens. So we would see like how efficiently has the model predicted the mask tokens. Now, since our model has predicted these particular tokens, these mask tokens, okay, we would be taking a look at the original tokens before masking, and the loss would be calculated based on how accurate these tokens were. Then, after the loss is calculated, the model's weights would be updated. And now we would be moving at step 2. Now at step 2, we would be further masking a few more tokens. Okay. So now again, we would repeat the process, ask the model to predict the mask tokens and again compute the weights. Step 3 would also be the same. At step 4, all the tokens would be masked. Okay. So all these tokens would be replaced by this particular mask token, and we would be asking a model to predict each and every mask token. Okay. Now, what I explained this training process, this is a sequential process. Okay. I explained it like a sequential process, so it would be easier. But when we actually train it, it is not sequential. Okay. So we randomly sample a step. Okay. And based on the step, let's say the step is 2, which is like halfway. So we would be masking half of the tokens randomly and then asking the model to predict the mask tokens. So this is how the entire diffusion language model works. Okay. And for the generation part, we would be taking a completely masked input sequence and ask it to denoise, just like in the image. Now let's take a look at how the generation of diffusion language model works and how it is different from traditional autoregressive models. So here I have a prompt. Okay. So let's say I want to ask this model, who is the president of India? So I would be giving the prompt inside this. Now, I have written this as a single word prompt, but this would be a sequence of tokens. Okay. Then we would start the beginning of sequence token and rest all the other tokens in the context window of our diffusion language model would be the mask token. Okay. Now the model would be starting at time step t equals to 1, and it will start the gradual denoising process. Okay. So in every step, it would generate probabilities of each of these masks. Okay. So we would be taking the highest probability mask and demasking it. By demasking, we would just be writing its corresponding token at this particular index. So let's say it would be randomly I'm taking anything. Okay. So at step 2, we would be unmasking half of these tokens. At step 3, we would be unmasking furthermore like 75% of these tokens. And by step 4, all of these tokens would be unmasked. And we would actually have the entire response. So this is how they are different from autoregressive model. Like we actually saw earlier, the autoregressive models work by first taking the first 2 tokens, then generating a new token, then taking these 2 tokens, these 3 tokens, generating another token. But diffusion models, they actually generate randomly. Like they attend to everything. They can see left and right. So they can kind of modify the tokens in the left and the right. But autoregressive models, they can only modify tokens in the right. Since we have our prerequisites clear, I would be jumping to the part where I actually explain what model I trained and what was my approach and intuition. Okay. So here I have used the Karpathy's Tiny Shakespeare dataset. Since this is small and I have used the Kaggle T4 GPU, so I have used intentionally a small dataset. Okay. So you can see the dataset has like 1 million characters roughly. And here I have made a custom tokenizer. the simple encode and decode functions. We have 70 as the vocab size, and the main mask ID is 4. Okay, I have explained the masking process. So what happens is when we actually mask the tokens, we replace the token, essentially the token ID with the mask ID. So every token ID, let's say to be and not to be, let's say I mask not. So the corresponding not token ID, 1, 2, 3, 4. So this 45th would be replaced with the fourth token with ID 4. Okay. So here I have defined the diffusion model. My diffusion model would have 32 steps. Since our data set is very small, I have decided to keep the diffusion steps less. Okay. So the model can only see, like, it would only have 32 diffusion steps in the generation process. Now, here I have my diffusion transformer language model code. Now, the diffusion transformer or language model is the same as your decoder only model, or let's take it the same as a GPT. Just the difference is we add a third line, which is time embedding. This is basically telling the model that which step are we actually on. Okay. And the second thing is that we do not add an attention mask. Now, usually in normal GPT, our model is not able to see the future tokens, but diffusion models can actually attend to the future tokens as well as the previous token. You can actually think of it like the BERT model. Actually, the BERT model is kind of the same as a diffusion language model, but the difference is the BERT model only has a fixed 15% masking, but a diffusion language model can go up to 100% masking. So here I've defined the diffusion model. It has 7 million parameters. Okay, here I have defined the dataset loader and dataset for training. Here I am using a batch size of 256. Pin memory equals to 2 for more memory efficient training. This kind of makes the training faster. So now in this part, we are actually training our model. First, I have switched the model from the CPU to the GPU, defined the optimizer. AdamW is the best optimizer for transformer related models. Here you can see the model architecture, and we are training it for 2000 steps. Here you can see the loss goes from 3.46. Actually, the first loss at 0 time step is not visible. The first loss at 0 time step was a lot, like 160 something, and gradually it came down to 1.83. Now, this is my model's output. Okay, so this in this function, this is diffusion infill. What essentially I have done is I have given it some random text, and we have masked like 50% and asked it to predict the original text, or basically unmask the original text. So this is the output. Obviously, it did not do a good job. And the main reason for this is that first we have used character level tokenization. Okay, as you can see, we have masked individual characters. Okay, so character level tokenization is inherently very difficult because first our vocabulary size is very less. So the model has to do a lot of work to actually make meaning. And here also you can see the model is trying to make a little bit of meaning, but since this is character level tokenization, you cannot actually see, or let me put it in easier terms, the model is doing a decent job, but since these are characters, even if like 25% of characters are long, it still looks like gibberish. Okay, but to make this better, what we can do further is give it a large text. A large text corpus. In this project, I have given it a very less text corpus because I wanted to train it and just, explore this text diffusion fields. I just gave it a very small or tiny Shakespeare text. But if I actually had given it a lot of text corpus, it could have performed a little bit better than this. Now, with this, we have actually reached to the end of this video. I just want to say thank you for watching this video. And Yeah, stay tuned for more content. I am still myself in my learning phase, and this is just a breakdown of what I understood and this whole project. Hope this was helpful and actually gave some insight. Thank you.